The first topic is a review of method of joints and method of sections. So first, let's have a bit of an introduction, definition of terms. So block is a structure composed of members passing together in such a way as to resist change in shape. What is that structure? Correct, Emmanuel? Yes. And Chloe, correct. The answer there is truss. So remember, in method of joints and method of sections, what we work on is a truss. So we have the following assumptions whenever we're talking about simple trusses. The first assumption is joints behave as smooth pins. So the members of a truss are joined together by means of a pin. And not only that, it can also be joined by riveting or welding to a gusset plate. Now, if due care is taken to assemble the bars or the members so that the center lines of the members intersect in a common point at each joint, the forces in the members may be calculated as if they were pin connected, even though their ends are actually riveted or welded to a gusset plate. Okay, so even though in actual it's not pin connected, if you did the assembly right, it can still be solved as a pin connected joint. Okay. Next, we have all loads are applied at joints. So trusses are constructed so that all applied loads act at the ends of the members, hence the joints. And then finally, weights of members are negligible. So they're negligible because otherwise they will create transverse loads. And transverse loads create bending stress and other types of stress, which is not analyzed in simple trusses. In that case, we have what we call a frame instead of a simple truss. That's why in truss analysis, weights are negligible. So in summary, for a truss, all the members are bar and elements. Okay? And these bar elements are loaded axially. So this means that a free body diagram of a typical member of a truss would show it acted upon by two equal, oppositely directed forces exerted by the pins at its ends. So to illustrate, let's have this. So let's say you have a truss. You saw the image earlier, right? Let me create a new one. So let's say we have this truss simply supported. So that means there's a pin and roller at these supports. And these are your joints A, B, C, D, E. Let's take member CD here. If I isolate that, it's going to look something like this. Okay? Okay. And when the assembly is done right, at the ends we have pin connections. And when there's pin connections, that means your member will be loaded axially. Okay, so it's going to look something like this. So these are the forces on your member, and they are actually equal in magnitude. So F. They're along the axis of your member, hence they're called axial forces. Now another term for that, and a better term is, these are called two force members. Okay. So once again, each bar element or member is known as a two-force member because if you isolate each member, and this is the free body diagram. So they are acted upon by two axial forces. And that will be a basis that we have when we talk about stresses in the future. So that's it for analysis of trusses. Now let's move on to the first method in analysis, which is method of joints. Now for method of joints, it involves concurrent force systems. Recall concurrent force systems are forces wherein they intersect at a common point. And then one thing about joints or method of joints is that when you're solving, you should select a joint with no more than two unknown forces involved. Okay, so no more than two. So keep that in mind as we go into our first example for method of joints. So example number 1, determine the forces in the members of the roof truss shown using method of joints. Okay, so basically I want to get force in member AB, BD, BC, AC, and CD. So let's start. Okay, so we have this drawing. So first, again, recall, you're gonna choose a joint with no more than two unknowns. Whenever we have a truss, you should start at one of these supports. Not always, okay, but typically you start at one of these supports because that is one of the easier reactions to take. So remember, whenever we have a support, there's support reactions. For a roller, the only reaction present is vertical or perpendicular to the surface. This is your surface, this is a roller. So now you can just assume the direction. I'm going to assume it's upward, okay? And perpendicular to the surface, and then let's call that RA. Here on point D, we have a pin. A pin has both perpendicular and parallel reactions because it can support or resist motion parallel and perpendicular. So we have two reactions here, and then similar to your roller, you're gonna assume direction. So I'm gonna assume the perpendicular portion of its reaction is upward, and then let's call that RDV because it's vertical. And then we have a parallel reaction. I'm gonna assume it's to the left simply because I have an external force here to the right. Remember, our structures are in equilibrium. So to cancel out this external right force, I need an internal reaction to the left. And then I'll call that RDH. So these are our reactions, okay? Now you can choose which joint we want to isolate first, okay? Upon looking at my drawing, RA has lesser unknowns than RD. So typically, I want to start with RA first so that there's only 3 forces to solve for. Okay, so I'll start with RA. Now again, another thing to keep in mind or to remember from your statics is whenever you're solving for reaction at a support for a truss, the method here is to use moment about the other support and equate it to 0. Okay, so if you want to take reaction at A, you take moment at D. If you want to take reaction at D, you take moment at A. Okay, so let's take moment at D. And this is an equilibrium equation. Okay, so this is one of the equilibrium equations. Later I'll ask you what the other two are. So first, moment equals 0. I take it at D. And now the step to solve for moment. Recall, moment equals force times distance. Okay, so you can start anywhere. I'll start with RA. Okay, so RA. Now next you have to figure out its sign. Okay, so for me, clockwise, that's positive. Counterclockwise is negative. Counterclockwise, negative. Okay. Now figure out RA rotated about D. That's clockwise. So positive RA. Now, it might be different from your past instructors. They could have positive as your counter, but for my lectures, keep in mind clockwise is positive. And you might have other methods to figure out if it's positive or negative, but for me, I just simply rotate it, like actually create a spiral following the direction of my assumption. So I assumed it's upward, so go upward and rotate about D. Hence, it creates a clockwise motion. So clockwise positive, okay? And then multiplied by the distance. So distance of RA, perpendicular distance to our moment center. We call D as your moment center in this equation. That's this line. And that's 8 plus 8. Therefore, this is 16. Okay. Next, we have 192. Similar to what I did here, rotate 192 about D. That creates a counterclockwise moment. So negative 192. And then multiplied by its perpendicular distance to D, and that's 8. So times 8. Next, we have 96. 96 actually passes through D. Now, whenever a force passes through your moment center, creates a moment of 0. So that means I can simply ignore these forces. Okay, so 96 passes through D, so I'll just ignore that. And then in the same way, RDV passes through D, RDH passes through D, so I'll ignore both of that. So there's no other force here. So now you can equate to 0. So from this, you can solve for RA. What's RA? Please solve. Correct, Pauline and Jan. Vico Fawny. So 96. If you've noticed, our answer is positive. Therefore, my assumption for RA is correct. So 96 kilonewton. Okay, so now we can reference that later on in our solution. So I know RA now. We've established earlier that I want to start at joint A. Okay. So let's start at joint A. So draw the free body diagram at joint A. So you have this. Okay. I like to draw the line of actions first. RA here is upward, so just copy that direction, RA. Now these lines represent your force in member AD and member AC. I like to label them as F sub AD, and then this would be F sub AC. Now we have to assume their direction. Now you can guess randomly, that's fine, or you can make an intelligent assumption. So to do that, look at what we have. I have RA, that's upward. Remember, this should be in equilibrium. So I need a downward force to balance this upward RA force. So therefore, I'll take that downward force from this line. So therefore, I'll point it downward. It's going to be this way. Now I have a force to the left because this is how I drew my direction. Therefore, I need a force to the right to balance that out, to put this into equilibrium. And I'll get that force to the right from my FAC. So I'll draw this to the right. Okay, so that's how you take intelligent assumptions. Hey, now we have this free body diagram. The next step is to use your equilibrium equations. The first equilibrium equation that we had is summation of moment equals 0. Can you give me the other equilibrium equations? Correct, John? Ry equals 0, or summation of forces y equals 0. What else? Okay, correct. Marino Sacro, and that is summation of x equals 0. Okay, summation of moment equals 0. Again, these are your equilibrium equations. Okay. So now you have a choice. This is just a concurrent force system, as mentioned earlier. Okay. They all intersect at a point. the only equations you can use for concurrent force systems are Fx, Fy equals 0. So you can start with either. Okay, it's fine, you'll get the answer eventually. But if you want to make your solution shorter, you can analyze first which equation will give me an answer immediately. So let's say I did summation of forces x first. Okay, FAB has an x component, FAC also has an x component. Both of them are unknown. Therefore, I can't solve for anything if I do that. Now, what if I do Fy equals 0? FAB and RA both have y components or y forces. However, I know RA, it's 96, so the only unknown is FAB. Therefore, I can immediately solve for FAB. So let's start with Fy. The summation of forces y or Ry equals 0. Okay. Now, sign convention here is upward and to the right, positive. Okay, downward to the left is your negative. This is upward, therefore positive RA. Next, FB or FAB is downward, so negative FAB. Now look here, it's diagonal. So it's not just simply upward or downward. There's a vertical and horizontal component. So we must get that. Now to get the vertical and horizontal component of FAB, you get its slope. Now one way to do that is looking at our original drawing. This is where your FAB lies. So if I get the slope of this, I can get the slope of FAB itself. Okay. So getting the slope, that's just getting your right triangle. Right? You can see we have a right triangle over here with base 8 and height 6. So you can copy that into our slope. Base 8, height 6. Now just have to solve for hypotenuse. What's the hypotenuse? Please solve. Correct, Emmanuel? Who else? And Jan. Okay, so everyone, please bring out your calculator to help solve in this problem solving. So 8, 6, 10. So I can copy that slope over here. So this 8, 6, 10. Now to get the vertical component, this is how you do it. Okay, copy the side that's also vertical since we're taking forces y. The side that's also vertical is 6. Okay, so copy 6 and then divide it by the hypotenuse, which is 10. And that's it. There's no other force here that has a vertical component, so equate that to 0. From this, you can solve for FAB. Please solve. What's the answer? Correct, Nicole? Who else? And LG? Oh, sorry, that's incorrect. Correct, John. The answer is 160. As you can see, it's positive, therefore, we have a correct assumption for direction. So you can just copy now the unit. Here it's kilonewton, so kilonewton. And then look at FAB. FAB is towards the joint, therefore that's compression. So that's the complete answer for internal force on each member. Okay, so if it's away from your joint, then you have something in tension. But since FAB is towards the joint, that's compression. Okay, so that's forces y. Now we can continue on summation of forces x. Okay, let's start. FAC is to the right, therefore positive FAC. Next, FAB is to the left, therefore that's negative FAB. Again, this is not directly just to the left, so I gotta get its horizontal component now. To get the horizontal component, just copy the horizontal side, so that's 8. And then again, divide by hypotenuse 10. This doesn't have a horizontal component, so there's nothing else. You can equate to 0. From this, I already know AB, 160. You can solve for FAC. Please solve. What's the answer? Correct. Pauline and Nicole. So Fanny Beltran. Again, our answer is 128. Positive. Therefore, correct assumption for direction. Just write out the unit. Our assumption is to the right, and that's away from the joint. Therefore, that's tension. There. Okay, now we're done with joint A. Now you have to move on to the next joint. And remember, you can only use joints where there's a maximum of 2 unknowns. Can you tell me one joint where there's only 2 unknowns now? Again, we're done with AB and AC. Okay, correct. The answers here are B and C. Because checking B, there's only 2 unknowns. Checking C, there's only 2 unknowns. However, at D, I haven't solved for RDV and RDH yet. So there's 4 unknowns for D. So now it's a matter of preference. You can start with B or C, whichever you want. Okay, let's try starting with B. So at B, again, draw. So you can start with drawing the lines first without the direction. Okay. And then this is your FAB, FBC, FBD. And then apply the directions we already know. I know FAB, it's in compression. So you have to draw it in compression again on the other joint. So this way. Okay. Now it's wrong to do this. Okay. Well, same direction, so same direction. No, that's not it. That's not what I mean. When I say the same direction, same compression or same tension. FAB is in compression, so this should be in compression as well. So this way, okay? So not the literal direction itself. So that's the only direction that I know. So now you can randomly guess, or you can make an intelligent guess. I have a force to the right. To balance this, I need a force to the left. So I'll take that from FBD. Okay, so I'll draw this to the left. Now I have 2 forces upward. I need a force downward to balance this. So I'll take that from FBC. So I'll draw this downward. And now you have your free body diagram. Next step is to do your equilibrium equation. Again, for concurrent force system, that's limited to summation of forces X and forces Y. So now you have to analyze which equation will give me an answer already. Let's check. If I did summation of forces Y, all of them have Y components. These 2 are still unknown, so I'll get 2 unknowns in one equation. Nothing to solve for yet. Now what if I do summation of forces X? Fx, these 2 are the only ones with horizontal components. So therefore, FBD is the only unknown, so I can solve for FBD. So therefore, let's start with summation of forces X equals 0. FAB is to the right, therefore positive FAB. And now it's not simply to the right, it's at an angle. So I gotta get its horizontal component. Now FAB is the same here, so you can just simply copy X 8, 6, 10. Or, okay, in some books, they're using the simplest form of this slope, which is dividing it by its common denominator. Common denominator here is 2. So divide everything by 2. Okay, 8 divided by 2, you get 4. 6 divided by 2, you get 3. 10 divided by 2, you get 5. So you can use the slope as well. Okay, they're the same thing. So therefore, we're using X. So FAB multiplied by horizontal side, which is 4, over hypotenuse 5. Next, This doesn't have a horizontal component. We have FBD to the left, so negative FBD, and get its horizontal component as well. FBD is over here. I'll get this slope. And we have another right triangle here with base 8, height 6. Okay, so I can draw that here as well, base 8, height 6. Or we can use that, or you can simplify already. 6 and 8 already have a common denominator, which is 2. So I'll divide them by 2. So this will become 4. 6 divided by 2, this will become 3. And now I can solve for hypotenuse. 3, 4, hypotenuse is 5. Okay? So it just happens to be the same slope as this. So I can copy that here again, 3, 4, 5. Once again, you can still use this, up to you. I'm just showing you what happens when we simplify the slope. So both of them are correct. Right, that's a slope. I need the x component, so get the horizontal side. So that's 4 over 5. There's no other 4, so equate to 0. Now this is easy to solve because 4 over 5 can cancel out. FBD is just equal to FAB. So FBD is just 160. Okay? Positive, therefore our assumption is correct. Our assumption for FBD is towards the point, therefore compression. So 160 kilonewton compression. And now we can move on to summation of forces Y equals 0. FAB upward, get the Y component, so get the vertical side, which is 3. So 3 over hypotenuse 5. Next, FBC is downward, so negative FBC. And then FBD upward, so positive FBD. Get its Y component again, so that's just copying the vertical side, which is 3 over hypotenuse 5. There's no other force, so I can just equate this now to 0. I know AB and BD. I can solve for BC. So please solve what's FBC. Correct. Maria and Joffrey, Aferos Cavero. Aferos. Cavero. So the answer is 192. Positive, therefore correct assumption. So just write 192 kilonewton. I assumed it's away from the joint, therefore that's tension. And now, yes, there's a question.
Question lang po.
Mhm.
With regards po dun sa FAB, ma'am, bakit po baliktad yung direction niya when it comes to joint B?
Because our assumption here is it's compression. So that is where we're copying it, not the actual literal direction. We're copying whether it's compression or tension. So this is compression, which means towards the joint. So therefore at B, it should be compression again, towards the joint.
Okay po, ma'am. Thank you po.
Okay, no problem. And again, for method of joints, when we have the same force that we solved for earlier, you're copying whether it's compression or tension, not the literal direction itself. So again, FAB, towards the joint, that means compression. Correct assumption. Okay, so you have to copy that compression again on the other joint. So here, this is your joint, so it should be in compression again, towards the joint. Okay? Again, copy compression or tension. All right, so that's A and B. And I've solved for BD and BC. So the only thing left is solving for CD. And we can do that by moving on to joint C, which is what we mentioned earlier. Okay, so now you can copy Okay, we have FAC over here. We have FBC here. Okay, and then we have FCD here. Okay, now apply your directions. FAC, tension. So I should draw it in tension again here. Again, tension means away from the joint. This is your joint, so away. So that's your FAC. Next, FBC also in tension. So I'll draw it in tension away from the joint. Okay. FCD, I don't know. So you can just assume. Okay. Let's say I made a random guess. I said to the left. Okay. So you can still do just random guesses. And now, if you've noticed, we have external forces. So whenever you're doing joints, don't forget the external forces and reactions. Okay, like we had RA here, so copy RA. Okay. The same manner, we have external forces here, so apply that as well. So we have a downward force of 192, and we have a force to the right of 96. So you can just do this. Okay, and now you have your free body diagram. Now recall, I only need to do or get FCD now. So use an equation that includes FCD. And what equation is that? Is it Fx or Fy that has CD in it? Correct? Jan and Cyrus, Tenorio, Vico. Oh, 2 points ka na pala. Next, Wells. 2 points ka na din. Correct, Ralph. Okay, the answer is summation of forces X. Correct. So, let's do that. Summation of forces X equals 0. FAC to the left, so negative FAC. 96 to the right, so positive 96. FCD to the left, so negative FCD. Equate that to 0. FAC is this. So you can solve for FCD. Please solve what's FCD. Correct, Cyrus? Wells. Correct, Maria. Maria? Maria. Christina. So Tenorio and Cabero. Tenorio. Cabero. There. It's negative 32. So negative 32, that negative just means I made an incorrect assumption in direction. So you should correct that in your final answer. FCD is 32 kilonewton. Initially, I assumed this as compression since it's towards the joint, right? That's incorrect. So your final answer should be the opposite of that, which is compression. Sorry. I initially assumed it's compression towards the joint. So your final answer should be the opposite, which is tension. Yeah. And that's it for method of joints. Now, if you want to practice, you can start with solving for reactions at D first. So you're going to take moment at A. You'll be able to solve for RDV and then do summation of forces horizontal equals 0 on the entire system. You'll get RDH. And then you can isolate B now because now these two are the only unknowns, and then work your way to the left. And you should get the same answers for everything. Okay? So that's it for method of joints. Do you have any questions so far? Please answer in the chat. Okay, no questions. Great. Let's move on to the next topic, which is method of sections. So for method of sections, we have non-concurrent force systems. These are forces that are neither concurrent nor parallel. So in contrast, your joints have concurrent. Here, method of sections, non-concurrent. And one thing to remember about method of sections, do not cut more than 3 members of the truss. So for method of joints, start with joints that have no more than 2 unknowns. Here for method of sections, do not cut more than 3 members of the truss. Okay, so keep that in mind as we solve for this problem. Determine the force in members BC, CE, and EF. Okay, so let's do that. Let me just copy that drawing. So method of sections. Let's copy these equations for our reference. Then this drawing. Okay. So again, what we want are forces in members BC, CE, EF. Now you can do method of joints. When you do method of joints, you solve for reactions at A or D, and then start at wherever you solve the reaction in. Let's say I solve for reaction at A, isolate A, you'll get these two, and then you can move on to B, you'll eventually get this, and then move on to E, you'll get this and this. Okay, so you can do that. Or you can do method of sections that just involves cut and isolating. So the only rule here is do not cut more than 3 members. And usually we want to cut where we want to solve the forces for. This is, or I want to get force on BC, EC, EF. That's not more than 3. So I can just cut that. I'll cut that. Cutting it here. So cut and then isolate. Okay, that's what it means when you isolate. So there. Okay. Now you can isolate either the left or right side after cutting. Up to you, your preference. Let's try cutting the right side. Okay. Now after cutting the right side, draw the resulting internal forces. Okay, so that happens wherever you cut a member. So I cut BC, so therefore force BC will arise. I cut member EC, so there's gonna be a force EC here. And then I cut EF, so there's gonna be a force EF. Okay. And then you can randomly guess, or you can make intelligent guesses on the directions of all of these, like what we did in method of joints. For me, my preference, I just like to assume everything in tension for method of joints, simply because that looks neater in my solution. Right? Again, it's up to you how you want to do that. Now, after doing that, we have a support here, and I have to solve for that support now. So this is a roller, therefore the only reaction is perpendicular to the surface. And I'll assume whether that reaction is upward or downward. I'm going to assume it's upward. And that's RD. Now I got to solve for RD. So that's solving for this. This is also RD. Remember, whenever we're getting reactions as a support, just take the moment on the other support. This is the other support, so I'll take moment about that point. So summation of moment at A equals 0. Okay, let's start. We have 50 here, rotate about A clockwise. So positive 50. Perpendicular distance is this, so that's 2. Next, we have 80. Again, rotate about A, that's clockwise, so positive 80. Perpendicular distance is, so to take perpendicular distance, you can just extend line of action. And then this is the perpendicular distance to A, which is 0.75. So 0.75. And then we have RD, rotate about A, that's counterclockwise, negative RD. Distance is this, so that's 1, 2, 3. There's no other force here. There's technically a reaction here for A. However, that reaction acts on A, so I can just ignore it, right? And then equate to 0. From this, you can solve what's RD. Correct. Ralph and Christian Denada. Denada. It's 53.33. Or you can also write the fraction of this, which is 160 over 3. And so for my subject, I want you to practice storing values in your calculator. Okay, so store. Just to have uniform answers. So to store, I have an Castro FX 991ES to store values. So you're going to get this 53.33. After getting that, we're going to hit Shift and then SPO. And then you have letters there in your calculator, A to F, and then you have XYM. So you can choose. Let's say I chose A, so shift store A. When you do that, your value 53.33 onwards will be stored in A. And now when you hit alpha A, it will bring up your 53.33. Okay? So please study how to store in your calculator because you might be using a different model than mine. Right, now after storing, we can now move on to the actual method of sections. So when doing method of sections, what you want to do is figure out an equation wherein there's only one unknown. Now remember, our equilibrium equations are as follows. So Fx, Fy, summation of moment. So can anyone tell me what equation should I use first, wherein there's only one unknown? Fx, Fy, and if you choose moment about what point then? Please answer in the chat. Very good, Nicole. The answer is summation of forces, y. Now there's another equation I'll show you later, but first we can start with summation of forces, y. Now let's double check. If we did fx, all these three have x components. So that's immediately three unknowns. Now what if we did fy? Only fec, or ce rather, let's do ce. Only for ce has a y component, so it's the only unknown. So that's why we can start with summation of forces y equals 0. Okay, so now let's begin. FCE, assume downward, so negative FCE. It's at an angle, so I gotta get its y component. Okay, so I gotta get this, which is this part. So again, look at the original drawing. See if you have a right triangle. I do. It's this one. Base 1, height 0.75. So 0.75. Hypotenuse, what's the hypotenuse of this? Correct, Christian? And Marino. 1.25. So you can just copy that here in your free body diagram, 0.75, 1.25. Okay, so now, again, we're doing Fy. So get y component, copy side that's also vertical. So that's 0.75. Over hypotenuse, 1.25. Okay, next. find other vertical forces in your diagram. We have a 50 here, downward, so negative 50. Next, RD, upward, so positive RD. There's no other force that has a vertical component, so just equate this to 0. Use the stored value of RD, which is whatever you use, or you can also just type in 160 over 3 for your RD. Doing that, please solve what's FC. Correct? Seth, Gabriel. And Janelle. 5.56. Very good. Now it's positive, therefore correct assumption. It's away from the member, so that's tension. So 5.56, don't forget the unit, kilonewton, and then direction, tension. Okay, so that's FCE. Now, we've established that forces X will create 3 unknowns, which is now just 2 unknowns since we already know CE. So we won't use that next. So the next equation would be a moment. So now my question is, where should I take my moment center so that the only unknown is 1, or the number of unknown is 1? So let me know which point. Again, the answer here is C, because remember, any force passing through your moment center will give a moment of 0. Okay, so FB, C, CE both pass through that, so that's 0. So the only unknown now would be FEF. So we can solve for FEF. Okay. So summation of moment about C equals 0. Let's start with EF. Rotate about C, that's clockwise. So positive FEF. Perpendicular distance is this, which is equal to 0.75. Next, 80. 80 also passes through C, so that's 0. What about 50? 50 also passes through C, so that's 0 again, right? So we're left with RD. Rotate RD about C, that's counterclockwise, so negative RD, and then get its perpendicular distance. So I'll just extend this line of action. This is the perpendicular distance to C, and that's 1 meter. So 1 equals 0. Considering RD again is 160 over 3, or using the stored value, you can solve for FEF. What is FEF? Correct, Mariah? But you're already 2 points. So next. Correct, Janelle. Correct, Jan. Correct, Ralph. Close. Correct, Tristan. De Los Reyes. And then correct, Elgene Meneses. The answer is 71.11. Again, it's positive. Therefore, correct assumption. Copy the unit, kilonewton. I assumed FEF away from the member, so that's in tension. Okay? And then now, since I know CE, EF, you can use summation of forces X equals 0, and then you'll get FBC. Okay, so you can do that. Now, what if I required you to use moment again? Okay, you're not allowed to use summation of forces X. So can anybody tell me where should I take my moment now so that I can solve for FBC? Okay, someone said F. only FEF passes through F. FCE does not pass through F at all. So not F. C, FBC also passes through C. So I cannot solve for FBC. Anywhere else? D. Only FEF passes through D. If I extend FCE, it doesn't pass through D at all. Think outside the box. Or quite literally, think outside this figure. What point where the other two forces meet? Okay, correct, Janelle and Christian. Danaga. Below. 3. Danaga. 3. The answer is E. Okay, because if you see here, this is E. CE and EF both intersect at E. So both of those will be canceled out. The only thing that will be left is BC. Okay, so for method of sections, you're not just confined to points in your isolated section. Okay, you can still extend that. So let's extend. Just don't include the forces. Okay. So extending, yeah. So you can do this. And this is your point E. Okay? So we can do summation of moment at E. Because again, FCE, FEF both pass through E. So I'm going to ignore that. Let's start with FBC. That's counterclockwise. So negative FBC. Next 50, rotate. That's again perpendicular distance to E. It's this, so that's 0.75. Next. -50, rotate about E, again counterclockwise. So negative 50, this is its perpendicular distance. You can refer to the original drawing, which is this. Distance of 50 from E is 1 meter. So 50 times 1. Okay? And then 80. 80, rotate about E, that's clockwise. So positive 80. Perpendicular distance to E is this, which is again 0.75. And finally, we have RD, rotate about E, that's counterclockwise. So negative RD. Perpendicular distance, again, you can refer to the original drawing. This is RD. Perpendicular distance is 2. So times 2. There's no other force. So we can already equate this to 0. Okay, and then from this, you can solve what's FBC. Oh, wait, sorry. 50 is actually clockwise, so this should be positive. Correction. Correct, Gabriel. Who else? For those who doesn't have a recitation point yet, please solve. Correct, Gabriel. 99 plus. Correct, Tristan. Okay, the answer is 4.44. Positive, therefore correct assumption again. So just copy the unit. And then, what is my direction? It's away from the point. Oh, wait lang. Okay. 4.44 kilonewton. Correct assumption. FBC is away towards away from the member, so that's tension. So T. And that's it. Now, if you want to practice, you can isolate the left side. So when you isolate the left side, you have to solve a reaction here, your pin reactions, and you should get the same answer as well. Okay. So that's it for method of sections. Do you have any questions so far? Please answer in the chat. Okay, no questions. Great. That ends our lecture for our review, method of sections, and method of joints.